Hello folks, this is lecture 1 on BGP, and in this lecture we'll just have an overview of BGP. Okay, first we'll start with some terms just to make sure that we're all on the same page. I've used these terms before, most of them. IGP, as you know, stands for Interior Gateway Protocol, and we mean the protocols you've studied to date, including RIP, EIGRP, OSPF, as well as others we've mentioned, or I've mentioned, like IGRP and IS to IS. But IGPs are the type of routing protocol that's used to exchange routing information inside or within an AS, or autonomous system. Contrasted to that is EGP, which stands for Exterior Gateway Protocol, and of them, the current one that's now still in use is called BGP, or Border Gateway Protocol, and it's the one that's used to exchange information between ASs and not inside one AS. An autonomous system itself, from RFC 1771, really is a set of routers under a single technical administration, and typically using an IGP inside and common metrics inside the AS, but then using an EGP, or Exterior Gateway Protocol, to route packets to other ASs. BGP, or Border Gateway Protocol itself, is what we call a path vector protocol, or sometimes called an advanced distance vector protocol. So just to drive home with this diagram the difference between IGPs versus EGPs, if you look at this diagram, we have a number of routers here in different ASs. So notice router A is an AS 64520, routers B and C are an AS 65000, and so forth. And in this diagram it's shown that BGP is running between them. So an AS is a collection of networks, as we said, under a single technical administration, while these IGPs operate within or inside an AS, whereas BGP, an Exterior Gateway Protocol, is used to route between these ASs. And as always, we're very cautious of route loops, and we don't want looping, and so we want the exchange of routing information to be loop free, and we want that to be guaranteed, and BGP does that for us. So when do we need to use BGP? Well, some of this information comes right from CCO, or Cisco Connection Online. So you use BGP when the effects of it are well understood, and one of the conditions here exists. If your AS allows packets to transit through it to reach another AS, in other words, your AS is what we call a transit AS. If your AS has multiple connections to other ASs, of course you must have multiple connections if you are a transit AS, and the flow of traffic entering or exiting your AS needs to be manipulated somehow based on some policies. And we'll talk more about what we mean by these policies. But based on the policy of how you want to carry the traffic and other attributes that actually live with these routes. So when do you not want to use BGP? Well, if any one of the following happens, if you've only got a single connection to the internet, or you're only singly connected to another AS, let's say your provider's AS, then you really don't need BGP. Or if you don't have any concern for routing policy or routing selection, also if you lack the resources, so the memory or processing power to handle BGP updates, then you definitely shouldn't run BGP, because otherwise your devices will be overwhelmed. Also, if your enterprise, the resourcing, so the human resourcing inside your enterprise, has a limited understanding of how to use BGP how to do route filtering with it and path selection, then absolutely do not use BGP, because it can really get you into trouble. And also, back to having a lot of routes coming in from BGP and the resourcing, if you have low bandwidth between your ASs, if those links between your ASs are low bandwidth, then you absolutely do not want to use BGP, because again, they will be overwhelmed. So who needs BGP? Not really as many networks as you may think, although of course anyone who's connected to the internet and has to provide transit traffic will absolutely have to do that. But again, it's fewer than you might think. Some of these quotes are from one of the references that I had mentioned in my course outline. It's a book by Jeff Doyle called Routing TCP/IP Volume 2. And so I'll just read them quickly. He says in his book, you should implement BGP only when a sound engineering reason compels you to do so, such as when the IGPs do not provide the tools necessary to implement the required routing policies, or when the size of the routing table cannot be controlled with summarization. The majority of the cases calling for BGP involve internet connectivity, either between a subscriber and an ISP, or more likely between ISPs. Yet even when interconnecting autonomous systems, BGP might be unnecessary. So this is really overall a warning to say, use it only when you need to use it, and make sure you know what you're doing when you're using it. So the next few slides we'll talk a little bit about autonomous systems. I want to be sure that you understand this. Autonomous system numbers, public AS numbers, have to be assigned just like public IP addresses. You have to register them, and there are a number of registries, just like, again, the registries from which you obtain IP addresses throughout the world, that are set up to do this. And the Internet Assigned Numbers Authority, or IANA, has allocated these public AS numbers to 5 of these global RIRs, or regional internet registries. So here I show a map of them, and the registry names are here. It's really, typically, this is really an acronym, of course, and on the right I show the areas that it covers. So it's color coded in this map, but basically from the pool of allocated AS numbers and IP addresses, these regional internet registries can further delegate some blocks to ISPs, and sometimes the large enterprises as well, who in turn will allocate them to customers. And the larger enterprises are called local internet registries, or LIRs. Then the end users themselves, who obtain their public IP addresses from their ISP, then are going to receive what we call a provider dependent allocation. In other words, internet traffic to them is going to be BGP routed to the ISP before being forwarded to the customer itself, because the IP addresses are provider dependent. Those IPs will always route to that provider and only that provider. Contrast that to users who are multi-homed to 2 or more providers. Then they need BGP routing directly to themselves and not to any specific provider. And so they must apply to the RIR in their region, of course, for provider independent IP addresses and a public AS number. So just backing up one bullet, the people or the enterprises who use provider dependent allocations, they don't need a public AS number, because all their traffic is going to be BGP routed to their only provider. Whereas the ones who are multi-homed, so these are the enterprises that want to have enough fault tolerance that if there's a problem at one provider, their traffic can keep flowing, if they're configured appropriately, to the other provider. That's of course why you would multi-home yourself, other than load balancing and so forth. So a little bit more on what we mean by ASs. Remember that an AS is a group of routers that share what we said it was a single technical administration. So they're going to share similar routing policies because they're in the same enterprise, and they're going to operate within a single administrative domain. Now, within an AS, these routers could be running a single IGP, but it could be a collection of routers running different protocols. They just all belong to one organization. And we actually discussed that when we talked about route redistribution, that there may be situations where you need to run more than one routing protocols in the same enterprise. In any case, from the outside, the world views that collection of routers as a single entity or a single autonomous system, or AS. So publicly anyway, each AS is identified by a single bit number. And as you know, a single 16-bit number, pardon me. And as you know, a 16-bit number has value from 0 to 65, 535 in decimal. So this chart, or this slide, is showing that the values from 1 to 64, 495, except for one special value, which we'll talk about shortly, are going to be assigned by an RIR or by IANA. Right after that range, we have a small range that's dedicated for documentation or sample code. Then there's another range that's reserved for private use. This is similar. This is for AS numbers, similar to how we have RFC 1918 addresses for private IP addresses. And then lastly, I'm showing you here that there are 3 specific values that are reserved and not assignable to any enterprise. So the very bottom of the range, 0, the very top of the range, 65, 535, and this special number in between, which we'll look at shortly. So because of the finite number of available AS numbers, an organization has to prevent justification before it will be assigned a public number. And now, more than ever, IANA is enforcing a policy where if you connect to a single provider and you share that provider's routing policies, in other words, you don't have your own policies and there's no need for them, then you're going to use an AS number from the private pool, and we'll look at how that happens later in this series of lectures on BGP. I've got a number of links here listed. I've posted these links on Blackboard. If I hover over them, let's see. Okay, I was hoping that a little bubble would show up with the number. It doesn't really matter. I have clicked these. Let me just bring my browser over into the recording window so you can see them. So one of these links, if you scroll down to the very end, this is the first one that shows the allocations. If you scroll down to the very bottom, and I'm scrolling back up a little bit here, this whole set essentially shows which ranges of which AS numbers have been assigned to which RIR. Now, you might notice, if you're really on the ball here, that I've got 16-bit numbers, but I've also got 32-bit numbers. And that's because, as you might have expected, we're running out of 16-bit numbers. And so we are now transitioning, or have been for a while actually, transitioning to 32-bit AS numbers. And I've also uploaded to Blackboard a white paper discussing that, but frankly it's outside the scope of what we want to talk about in this course. But that special number that we looked at before, 2, 3, 4, 5, 6, that AS number is actually called AS trans, and it's used for the 16 to 32-bit transition. So if you're interested, have a look at RFC 4893, which discusses that, and also the white paper I've uploaded to Blackboard. The other link here, 16-bit ASN usage, and I'll bring my browser window back in here. shows how much of the entire space has been used. And so notice that really most of the space has been allocated according to this. You can see this chart here out of the 16-bit AS number pool. In fact, at this moment, only just less than 200 AS numbers are free and exist in the pool to be allocated. A number of them are reserved for IETF usage. I believe that actually it does include the private number space as well. But notice up here it says that, and this is current to today, the 11th of November 2015. Notice here that they're saying the data available suggests the best fit predictive model where the numbers will run out 18th of July 2017 based on the current trend of the frequency of allocation. Okay, let's go on. So now we're going to look at a few scenarios where you may or may not use BGP and how your enterprise might connect to a provider and to the internet. So the simplest one, of course, is a single homed AS using a default route. And we've used this one a lot because that is the simplest model. So in this circumstance, then you've got a customer network where you've got a single exit point to outside networks, and it's a single home system, sometimes referred to as a stub network as far as the ISP is concerned, where this customer is a stub network. And so that stub relies on a default route to handle all the traffic that's going out of its local networks. So in this situation then, BGP is not normally needed. So notice what we've got going here, and I'm sure you've seen this time and again. We've got a default route leading out of the CE, the customer edge, to the PE, and the PE has a static route coming back for all the public numbers, all the public IP addresses that would be registered for that customer, right? So in this case, we would have provider dependent space because the ISP is the only link to the outside world, to the internet. And so the internet out here somewhere where my mouse is moving will route all the traffic to the provider's numbers first through BGP, and then once inside the provider's space, the provider knows to route it back to this PE router, which is connected to the CE router, and at that point the static route takes over and the traffic can be handed back to the customer network. The next scenario is still a single homed AS, but in this particular example now, there's some reason for the provider to have more detailed routing information for the customer networks. So in that case, then the ISP may well run an IGP, a common IGP with the customer. And so in this case, we're looking at running OSPF, let's say, and there's an OSPF peering between the CE and the PE. And so the CE sends detailed routes to the PE, and the PE sends a default route to the CE. So we still want to route using the default route out, but the provider has the detailed routes of what is going on inside here. So this situation, normally no BGP required. The next example is still a single homed AS, but in this example we are using BGP between the provider and the customer network. So in this example, the customer has some routing policies they want to enforce, and since they're only single homed to a provider, then the provider can run BGP with this customer, but instead of assigning a public AS number to that customer, the provider will then just use a private AS number, so from the private pool. Remember we said these were like private IP addresses from RFC 1918 that you're used to. And what happens in this case then is that through this peering, the customer can enforce routing policies to either accept or reject certain routes provided by the ISP. So the customer can use some of them now dynamically. Instead of just a default route, the customer can get some dynamic routes from the provider. Meanwhile, as the customer advertises networks out via BGP to the provider, then the provider can turn around and in turn advertise that out to the rest of the internet. But the provider will filter out the AS numbers because you don't want private AS numbers leaking out to the internet, just like we don't want private IP addresses leaking out to the internet. In this next example, now we're dual homed. So notice in this situation we've actually got three slightly different options. In the first one, we've got two links. Well, we've got two links in every case, but we've got two links to the same provider and the same router at the provider. So this gives us link redundancy, but of course it does not give us device redundancy. The next option then, before I go on and talk about that, so really in terms of routing options, we've got the same routing options that we discussed for single home, because we still really have one provider, but now we've got multiple links to the same provider. Of course, other advantages include the ability to do load balancing and maybe to have a primary link and then a backup link in terms of routing policy, which one you would prefer to use. Maybe because you're being tariffed differently, so one link might cost you less money than the other one. So three different options, as I said. In the second option, you notice now we've got device redundancy at the enterprise, so we've got two different CEs, but we're still being connected to the same PE. Whereas in option 3, we've got a doubling of both the CE end of things as well as the PE end of things, which of course is ideal. More expensive, of course, in terms of resourcing, but certainly better fault tolerance. So now the next example is where we've got multi-homing but using a single link. And you've got one link per provider, and now we're multi-home, so we have two or more providers. Now, as soon as you have multiple providers like this, then typically you will be running BGP. And so in terms of exchanging routes, you have the option of exchanging full internet routes with each provider, and that would be upwards of over 500,000 routes. So actually I'll show you a graph of the current number of active BGP routes out on the internet. I think it's graphically it's approaching something like 575,000 now. But just to get a sense of what it takes to hold this many routes, approximately in a Cisco iOS router you're looking at about 70 megabytes of RAM to hold 100,000 BGP routes, give or take. The other option you have is that you could take one provider and have full internet routes through one, and then through the other one maybe it's just your backup provider, and so you might have only partial updates to selected destinations through that provider. Now, what do we mean by that? Well, one obvious way is to say, well, that really is my backup link, but because I know that other provider will route faster to its customers, then only over this secondary link for the customers that are directly connected to ISP2, I will route this way. Otherwise, I'll always use the other one because it's really this second ISP, excuse me, is really just my backup one. So that's one way to have a policy. Another thing you can do is you could have partial updates with one of them, again, selected destinations, whereas the other side then is your default route. Meaning what? Well, meaning if you've got more specific routes, it'll take that other one, and instead of trying to manage all the routes from the internet through your primary provider, you just use a default route. Now that's a little bit more dangerous because in the case where you have full internet routes, if you're trying to route to an enterprise on the internet that has lost connection to ISP1 somehow, maybe it's not even ISP1's fault. It could be, somebody in between. But basically, if your destination has lost connection somehow to that, but it has still got a good connection through your other one, but it wasn't part of your policy for your partial updates, then you're still not going to be able to get to that destination. Routing will still fail. So you want to be cautious about doing this, but certainly it saves you a lot of resources, right, if you don't have to have full internet routes anywhere in your enterprise. And the last one we'll talk about is where we've got dual links, or maybe even more than 2 links, to each provider. And this, of course, gives us much better resiliency. And so in this scenario, you can see the couple of pictures I have here. Similar options again as the single multi-homed in terms of full internet routes or partial routes. But of course, we've got now multi-home, so definitely enhanced resiliency. Oops, sorry. And notice how in the first case on the left, I've got 2 links to each provider like this, but to make it even more broadly based, each of our CE routers could be having 1 link to each of the routers on the PE side, right? So this gives us quite a bit of failover, because not only now can we load balance across 2 devices at the customer end of it, but each one of those is not dependent on any single provider. So we've got 2 providers on each of our CE. And of course, if we can convince the provider to also use different devices on the other end, then we've enhanced again our fault tolerance. So when we're multi-home, I just want to draw attention to what we talked about in OSPF. Remember, we talked about the fact that we have E1 routes and E2 routes. So look at this example. We've got dual homing, we've got 2 CE routers, to the same provider, let's say. And it could be the same or it could be different providers. It really depends. It doesn't really matter. The point I'm trying to make here is that I'm trying to show you the difference between when we would use E1 versus E2. So in this example, one option might be just to use 1 link as a primary link and the other one as backup. And so if you really wanted to do that, then what you would do is you would bring both of them in as E2 routes, because remember, E2 routes don't aggregate the interior cost inside OSPF. So as they're being brought in, they're both E2. But the one you really want to use as the primary link, then you want to seed that at a lower cost, right? Because then that'll be more preferred. However, that would really leave one mostly unused, and so to reduce the risk of congestion, let's say, a better design would be to use both paths simultaneously, as long as you're paying for both, right? I'm assuming here you don't have the situation where you have a primary path and your secondary path is costing you money only when you use it. So not that situation. Okay, so if you do this, then what you could do to use both paths is to bring both in as E1. And that way, whichever router has the shortest path or lowest cost to that exit point will use that exit point. You see? And that way you can use the interior costing to route you to the best exit point in terms of the least cost one. And surprisingly, in many cases, this will be sufficient for good internetwork performance. Now, the problem with that, as soon as you have multiple links that are active, of course, is that if you've got stateful firewalls, then your traffic might not necessarily return the same way that it went out. So you have to be careful about that. So if you've got a multi-home non-transit AS, remember, we're doing that so that we have our own fault tolerance or resiliency, right? A transit AS is going to carry traffic originating and destined for foreign networks. A non-transit AS only carries traffic originating from or destined for the network itself, or that AS itself. Also, a non-transit AS will advertise only its own routes to both providers. It will not advertise routes learned from one provider into the other one. We'll talk more about that later, because the principle this is based on, by the way, is something I've mentioned before, and that is that every time you advertise a route, you're promising to carry traffic. So if this AS24 advertises its routes towards ISP2, then anyone at ISP2 and beyond it is eligible to send traffic towards you for those routes, right? You're promising to carry the traffic. So that's why we say here it advertises only its own routes, because if AS24 received routes from ISP1 and started advertising them out towards ISP2, that would draw traffic through ISP2 towards AS24 that was destined for ISP1, and that would be something we don't want, because that would turn that AS24 into a transit AS. So this is why my last bullet here says, in our example then, if AS24 advertises only its own routes to both providers, then this ensures that ISP1 will not use AS24 to reach destinations belonging to the other ISP, ISP2, nor vice versa. So similarly, ISP2 wouldn't use AS24 to reach destinations belonging to ISP1. So, still talking about multi-home non-transit AS there. Now remember, and I put this up here on the right, remember any enterprise that's multi-home, that's connected to 2 or more ISPs, must use provider independent IP address space, right? But if you're multi-home, then you're non-transit, then you don't necessarily need to run BGP. But it is usually recommended, and some ISPs will require it, because it allows you increased control over propagating of routes, and you can then enact some policies for where you send your traffic and which provider you prefer. So this is why I say here that BGP route selections is rooted in your enterprise policies. So again, remember, if you accept full internet BGP routing, you're talking about over 500,000 routes. So to compare, in January of 2003, there were about 140,000 BGP routes in the internet. Now, there are more than 500,000. So I'll just bring up my browser here, and you can see the link up here. This is bgp.potoroo.net. This is a graph that's showing how many BGP routing information based entries there are now. So see, the number is approaching 600,000. This is the year down here. So okay. So if you can help it, do consider partial BGP routes, meaning you're only accepting routes to providers, other subscribers, and maybe you can make use of default routing to get your reachability anywhere else. So when you're using BGP more than ever now, you want to think about routing as 2 logical links. So what we mean by that is that incoming route advertisements are going to influence your outgoing traffic, and outgoing advertisements will influence your incoming traffic. So remember what I said, that if you advertise a route out, you're going to draw traffic towards you, because your outgoing advertisements will influence what comes towards you. But similarly, in the other direction, the incoming route advertisements will influence how you send your outgoing traffic, because you wouldn't be sending traffic out unless you had a route, even if that was a default route. Okay, so you want to consider your external traffic as actually being on separate logical links. Your ingress traffic coming towards you is resulting from routes you advertise. So routes advertised by your AS to your provider. Whereas your egress traffic will only result from routes accepted into your AS from your provider. Or it could be default routes, but it's really the same thing, because the provider is allowing you to send everything by default to them, right? So the default routes, then you will advertise from your boundary router right at the border, and what metrics you use to draw what traffic towards which exit point in your enterprise. So if the provider actually advertises routes into your AS via BGP, then your internal routers will have more accurate information about what's the best exit point to reach external destinations, if you happen to have more than one route to the same destination. And if your internal routes are advertised to the provider via BGP, then you can influence by which route you advertise, at which point you'll draw traffic towards you into your enterprise. And BGP will also provide tools to some degree to influence the choices your provider makes. You can send attributes to your provider to influence how they route traffic to you. And we'll look at that later. So we've been talking about non-transit systems. So let's say we've got a transit system now, or transit AS. So here in this picture, consider now if this is a multi-home transit AS with more than one connection to the outside world, then from the point of view of the multi-home AS, transit traffic, remember, is any traffic originating from outside sources bound for outside sources. So ISP2's customers, in addition to ISP2 themselves, can transit through your AS 24 here through this link and out to another internet destination, including ISP1. That's what makes you a transit AS, and vice versa, of course, going the other way. So still on this particular topology, then when BGP is running between routers inside your AS in order to pass those routes along, then it's referred to as internal BGP or IBGP. When you've got BGP running between routers outside your enterprise, so from different AS numbers, then we call that external BGP or EBGP. And in terms of terminology, if the role of a BGP router is to route IBGP traffic, we call that a transit router as well. So remember, routers that sit on the boundary, we call these border routers or edge routers, right? And by definition, these are going to run EBGP with routers from another AS. So we're going to finish this short lecture by looking at some I guess warnings or caveats. Creating a BGP peering relationship involves really a combination of trust and mistrust. By that we mean that, like it or not, you must trust the network administrator on the other side to know what they're doing, because you have to trust that things will work well the way you have configured your connection to that other router. But at the same time, you will need to take every precaution, every practical measure to protect yourself in the event that the other side does make a mistake. So this is why this is a common sort of concept that paranoia is your friend when you're running BGP. So some hazards, back to the Doyle book that I spoke of earlier, regarding TCP/IP Volume 2. These are some of the warnings from Doyle. So your provider will show little patience with you if you make mistakes in your BGP configuration. Suppose, for example, that through some mistake you've made, you start advertising 207.46.00/16 to your provider. And on the receiving side, if the provider hasn't tried to filter this out and somehow allows it to be advertised upstream to the rest of the internet, well, this particular CIDR block belongs to Microsoft. So if you've just claimed to have a route, then you could start drawing traffic for that whole /16 towards you. And as you start doing that, of course, you can't deliver it. Then a significant portion of the internet community then could decide to use that path towards you, thinking you're the best route. You get all these unwanted packets through your internet connection, which swamps your connection, but more importantly, you will be black holing traffic that should really have gone to Microsoft. And when they start losing their traffic, then no one's going to be amused, nor will they be understanding. So this is what we mean about, you have to trust the other guy, but you have to take some precautions. So in this case, for example, your provider should probably have done something here to limit what you can advertise through him. That's done all the time. So earlier we were talking about being a non-transit versus a transit network. So I had already alluded to this, but this is my final slide in this introductory overview lecture. If you do inadvertently advertise routes learned, let's say, from the right side here, ISP2, towards ISP1, well, then ISP1 and its customers will see possibly our AS24 network as being the best path towards ISP2 or its customers, and all of a sudden now we'll be carrying transit traffic. So in the example in the previous slide, I mentioned maybe you start black holing Microsoft traffic. Well, here you may not be black holing any traffic, but now you've become part of the core of the internet, routing internet traffic on your own networks, using up your own links and your own device resources and so forth, which you usually don't want to do unless you've made some kind of deal to do that. So this is the kind of trouble you can get into if you don't configure BGP properly. And that's the end of my overview lecture. The next one will be on some BGP basics.